All right. Hey, everybody. Welcome back. Today, we are going to be shifting gears just a little bit and talking about an object called a Taylor polynomial. Our goal in this video is to introduce what a Taylor polynomial is, draw some connections between this object and the thing that we saw, in Calc 1, the linear approximation, and we'll work through an explicit example together. Okay, so first of all, for motivation, let's remember what the linear approximation of a function was. So the linear approximation was always defined for a given function f of x around a point x equals a, right? And it was defined as the best approximation, or the line that best approximated the function f of x near the point a. And so as sort of a drawing example, let's say we have a function, this is f of x, and let's say that maybe this point right here is our point A. Then visually, the linear approximation is supposed to be the line that both touches the function at the point a comma f of a, and also maybe hugs the function closely there. So we'd end up with something that looks kind of like this, right? And this would be the L of x. Right now, to define this line, we could use the point slope form of a line. We know that this point, or that this line, crosses through the point a comma f of a, right? So that's the point a comma f of a. And we know that this line has the slope given by y equals f prime of x, right? And so with those two pieces of information and with the point slope form of a line, we can rewrite our equation for our line, or our L of x, in this form right here. Now, we said that this was the best approximation for the function f of x, or the line that best approximated it, because in a certain sense, first of all, visually, it is the line that seems to hug the function as closely as possible. And if I were to zoom in on the picture right here, it looks like the line and the function are sort of traveling very, very close to each other. But we can also make the observation that at the point x equals a, not only do we have L of a equals f of a, right? And that's true because if I plugged in a, this term would just disappear, right? We would get 0. So L of a would equal f of a, but we also get that L prime of a equals f prime of a, right? So these two functions agree at the point and in the first derivative at the point. Okay, great. So that was our linear approximation. And now we turn our attention to something called a Taylor polynomial. And it turns out that a Taylor polynomial will be a generalization of the linear approximation. So the nth Taylor polynomial for a function f centered at a point a for any value n is of the following form, right? So p sub n of x, that's what we will call our nth Taylor polynomial, so that's just its name. That's the nth Taylor polynomial, right? And that's going to be defined as f of a plus, and then we see the following pattern here. So we get f prime of a over 1 factorial times x minus a plus f double prime of a over 2 factorial times x minus a squared, plus the next term would be f triple prime of a, so the third derivative of f at a, over 3 factorial times x minus a cubed, plus dot, 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 all the way up to the nth term, in which we take the nth derivative of f at the point a divided by n factorial times x minus a raised to the n power. And so if I wanted to write this in sum notation, right, this is really the sum as k goes from, let's say, 0 to infinity of the kth derivative of f at a divided by k factorial times x minus a to the k, right? And we can see that when k equals 1, we get this term, right? The first derivative of a over 1 factorial times x minus a to the first, right? So there's secretly a 1 here. We are using a few specific conventions here. Specifically, we are saying that if I took the 0th derivative of our function at a, that just equals f of a. So the 0th derivative is just the function itself. And we are using the convention that 0 factorial is equal to 1. And oftentimes in mathematics textbooks, we'll just define 0 factorial to equal 1. So in that case, we can rewrite this first term as f to the 0 of a over 0 factorial times x minus a to the 0. The x minus a to the 0 would just become a 1. And in that way, this satisfies this rule. And I realize I've actually written something incorrectly here, which is a little sloppy and maybe a little bit of foreshadowing. This should just be the sum as k goes from 0 to n, right? Because we're starting with the 0th term and we're going up to the nth term. Okay, great. So when a is equal to 0, right? So when we choose to create a Taylor polynomial for a function f of x centered at the number 0, our formula simplifies a little bit. Specifically, all of these x minus a's, they just become x's. And so the resulting polynomial expression that we get is often called a Maclaurin polynomial. It's just a special version of Taylor polynomial. And notice the formula we have here is exactly the same as the one above, except we're plugging in a equals 0. And because we're plugging in a equals 0, our x minus a's just become x's, right? And our Maclaurin polynomial has the nice form where p sub n of x equals the sum as k goes from 0 to n of f of 0 over k factorial. That should be f sub n of 0, so the nth derivative of f at 0. The kth derivative of f at 0 over k factorial times x to the k. All right, so really we get identical formulas, except we're plugging in 0 instead of a. Okay, so that is the formula that we get. Let's do ourselves a favor and work through some initial examples. So let's find the first few Maclaurin polynomials for the function f of x equals sine of x. So as a reminder, the Maclaurin polynomial was the polynomial that was centered at 0. So we're going to need to record some information here specifically about the derivatives of the sine function at 0. And I'm going to do that off to the left here. Okay, so on the left, we know that sine of 0 is equal to 0. We know that when we take the first derivative of sine, right? So the first derivative of sine equals cosine. And so cosine of 0 is equal to 0. Nope, cosine of 0 is equal to 1. The second derivative of sine, right? And we'll compute the first several of these. So the second derivative of sine is equal to negative sine. And negative sine of 0 is equal to 0. Let's do one more. The third derivative of sine is going to be the derivative of negative sine, so that's negative cosine. And when we plug in 0, the negative cosine of 0 will be negative 1. All right, great. So armed with that information, we can recognize that p sub x, p sub 0 of x, right? So the 0th order Taylor polynomial is just going to be 0. The first order Taylor polynomial, right? So again, that will end up being 0 plus, and then we'll take whatever we got here, right? So this is the first derivative of our function evaluated at 0. And so that will be 1 divided by 1 factorial times x, right? Or it would be x minus a to the first. In this case, that's just x minus 0 to the first, so it's just x. And so simplified, that becomes p sub 1 of x equals x. P sub 2 of x, well, that would be 0 plus x plus, and then we get our third term, right? Or our term that corresponds with the second derivative. So that would again be 0. Formally, that would be 0 divided by 2 factorial times x squared. But of course, the 0 is there, which just means that p2 of x equals x. And p3 of x, well, p3 of x will be the previous polynomial. So that's 0 plus x plus 0 plus, and then we'll use this third derivative right here, right? And so this third derivative will end up with a -1. So that will end up being a -1 over 3 factorial times x cubed, right? And so that can all simplify down. P3 of x equals x minus 1 over, now let's think, 3 factorial is equal to 6, right? 3 times 2 times 1 times x cubed. And so we end up getting these results for our first several Taylor polynomials. P sub 1 of x equals x, and P sub 3 of x, the next non-zero one, or the next new one, is x minus 1/6 x cubed. And so these are the Taylor polynomials that we begin to see. All right. Okay, and so I wanted to end this video really quickly just by showing you what these different Taylor polynomials might look like. So here in sort of graphed in black ink, we have our function f of x equals sine of x. And here's our first Taylor polynomial, our p sub 1, which was just p sub 1 of x equals x. Right? Notice this is the same thing as the linear approximation. It's going to be that line that best hugs the function sine of x. If I wanted to bump up to my third order Taylor polynomial, so that was x minus 1/6 x cubed, well, this is what that looks like. And notice this third order polynomial continues to hug the sine function really, really well. If I wanted to bump up to the fifth order Taylor polynomial, I get this quintic polynomial, this degree 5 polynomial. And if I wanted to bump up to degree 7, I get this polynomial. And if I wanted to bump up to degree 9, I get this polynomial, right? So by following this form of Taylor polynomials, or I should say by calculating these Taylor polynomials, I am getting a better and better and better Taylor approximation, or a better and better approximation to the original function. And we'll explore the nature of this approximation and the relationship between the polynomial and the Taylor approximation in the next video. So thanks so much, everybody. I'll see you next time.